Now we are moving into 11.8, power series. In chapter 11, we've been dealing with a lot of different types of series and series testing. However, nearly everything that we have been discussing so far was about the series of numbers, the series of real numbers to be a little bit more precise. From this point on the other hand, we are going to consider functions defined by infinite series. And the easiest of such examples is a power series. What is a power series? It's a kind of function defined, well, kind of like these. Summation n is running from 0 to infinity, an x to the nth power, or in a little bit more general, n is running from 0 to infinity, an x minus c to the nth power. I hope everybody can easily see that the second expression is a little bit more general than the first one, in a sense that if you plug in c equals 0, and consequently, if this highlighted part drops out, then we have the first expression, This number c, by the way, is called the center of the power series. And that's why I'm using the character c for this. The reason it is called the center is because the domain of the power series function will turn out to be an interval centered at c. And that interval is called the interval of convergence, and that's one of the three important topics of this section and the next. For now, let's come back to the definition and lingos. And let's make one more observation. If you change this infinite sum into a finite sum, in other words, if we have something like that, then what do you see? We have nothing more than a polynomial function, a polynomial of degree capital N, provided that the leading coefficient a capital N is non-zero. In other words, we can regard that the power series function is a natural extension of a polynomial function, and thus they share the same terminologies. Just like polynomial functions, this kind of thing is called a term, an x to the nth power. In this particular case, you're looking at a cubic term, and this is a quadratic term, and this is a linear term, constant term, and this kind of thing is general term, and so on, nth term. And each an's are called coefficients, just like polynomials. C, we already talked about what C is. It's a center of the power series, or we say the power series is centered at C. Please remember these terminologies. Now that we talked about the power series function, we have to talk about its domain. In other words, what is the set in which this power series expression makes sense? It'll turn out that domain is an interval centered at C, which we call the interval of convergence. However, there's a bit of a theoretical subtlety here. How do you know this is an interval, and how do you know that it exists, and so on? As a matter of fact, that's what Theorem 1.2 is all about. It certifies that the domain of the power series function is an interval centered at C, and also it introduces a concept called the radius of convergence. The full proof is here, but it's rather complicated, rather deep, as you can probably see. And I'm not going to talk about it in this video. Maybe in an optional video I may, but not here, certainly. For now, let us just take Theorem 1.2 for granted, and let us assume that the domain of a power series function is indeed an interval centered at C. In other words, the interval of convergence exists, and then let's do computation problems about it, assuming the existence. The key technique we're going to be using will be the ratio test. Sometimes we may have to use the root test, but that's rare. Most of the time it's going to be the ratio test. Here's a reminder, what is a ratio test? Well, here it is. We take the limit of the ratio of the next term over the current term, or an plus 1 over an, and take the limit of the absolute value of the ratio. If that limit is less than 1, then we have absolute convergence. Greater than 1, then we have divergence. And equals to 1, then the ratio test fails. We must find alternative methods, or methods in plural. So please remember these. We have to take the nth term over the n plus first term over the nth term, And that's what we are going to do for problem 1.4a. Let's expand the font a little bit, and then here it is. The nth term goes to the denominator, and then the n plus first term comes to the numerator. All I have to do is to change all the n's to n plus 1. And now, do you see a cancellation? Absolute value of x to the n plus first power over the absolute value of x to the nth power will cancel each other out, and I'm going to get only the absolute value of x. How about the number part? Well, that's just routine limit computation problem, to tell the truth. Divide everything by 3 to the nth power, and what you get? 2/3 to the nth power, which goes to 0. This plus 1 will survive, and then 2/3 to the nth power will become 0, and this plus 3 will survive. In the end, what do we get? 1/3 times the absolute value of x. And this is the L value of the ratio test, the limit of the absolute value of the ratio. Now, if this is less than 1 in absolute value, then we have absolute convergence. Greater than that 1, then we have divergence. Equal to 1, we have to do something more. And here we go. Take this one less than 1. In other words, without absolute value, x over 3 is between -1 and +1. And algebraically, we can solve it. We have an open interval, -3 to +3. That's where we have the absolute convergence. And now, outside, or rather, in the exterior of this interval, we have divergence. At the end point, at x equal to -3 and at x equal to 3, well, ratio test does not apply, so we have to use some alternative method manually. Plug in x equal to -3, and we have this numerical series. It turns out this time it's the nth term test for divergence, because the general term does not go to 0. If you plug in x equal to 3, then again we have this kind of numerical series. Same technique applies. Nth term test for divergence applies, and then we conclude that the series diverges at x equal to -3 and also at x equals to +3. Consequently, what we have, the interval of convergence is the open interval -3, 3. Is this really a typical case? To a certain degree it is. This kind of cancellation of absolute values and then absolute value of x showing up in the end, that's typical. About the endpoints, that's not really typical. You can have various different type of cases. Here's an example, if I remember correctly, that we have a closed interval. Okay, let's apply the ratio test again. The general term goes to the denominator, and the numerator is occupied by the n plus first term. Oh, come on. Okay. The numerator is n plus first term, obtained by replacing all the n's by n plus 1. Now, do you see the cancellation as before? Absolute value of 5 minus x to the n plus first power over the absolute value of 5 minus x to the nth power. And after cancellation, we're going to get absolute value of 5 minus x. There's one more. 4 to the n plus first power and 4 to the nth power. We have cancellation, and then we have 4 in the denominator. In general, we have this highlighted expression. How about the other n parts? Well, the other part, which can be simplified like this, is a purely algebraic part. And the growth order for numerator and denominator are both 4. You can easily find out this limit. This plus 1, the second plus 1, and third plus 1, and then the last plus 1 will drop out. We are going to get basically n to the 4th power over n to the 4th power asymptotically. So the limit is 1. In short, the limit of the ratio is this absolute value of 5 minus x over 4, and if that's less than 1, we have absolute convergence. In short, we have 5 minus x over 4 is between -1 and +1. Solving this inequality, we get this open interval 1, 9. In the exterior of this open interval, we have divergence. How about the endpoints? Plug in x equals 1 and plug in x equal to 9. If you plug in x equals 1 to the, then we have 5 minus 1 to the nth power, which is 4 to the nth power, which cancel out this denominator. And what we have, we just have an algebraic infinite series. So asymptotically, this algebraic series is asymptotically equivalent to a p series 1 over n squared. We're going to have a convergence, or absolute convergence to be a little bit more precise. And you can do the same thing by plugging x equals to 9. We have 5 minus 9 to the nth power, -4 to the nth power, that is. After cancellation, we get this numerical series. You can do the same thing. This is an alternating series, yes, but the absolute value will give you convergence because asymptotically, the absolute value is equivalent to 1 over n squared series. We have absolute convergence for both. In short, we have the interval of convergence as this. The closed interval 1, 9. Both x equals 1 and x equal to 9 are valid as far as the convergence is concerned. There are some other cases where only one of them is valid, and we may end up with half open, half closed interval. And if I remember correctly, this is the one. Let's do it. As usual, the general term goes to denominator, and k plus first term goes to the numerator. After simplification, we have absolute value of 3 minus 2x. And then how about all those k terms? Well, k over k plus 1, that's going to 1. And then log of k over log of k plus 1, that also goes to 1. So the limit of the ratio is just 1 times this absolute value. So what do we end up with this kind of algebraic inequality, and we end up with the interval, the interior of the interval, open interval 1, 2. In the exterior, we have divergence. At the end point, we have to test them manually. When x is equal to 1, what do you get? We have 3 minus 2 to the k power, so we just have just 1 in numerator. What do we get? We have this positive series, and integral test applies, and we have divergence toward infinity. What if we plug in x is equal to 2? Then the numerator will be 3 minus 4 to the k power, so we end up with an alternating series here. And the absolute value goes down to 0. What do you get? We have convergence because this is an alternating series whose absolute value decreased to 0. So what we have in the end, we have a half open, half closed interval 1, 2, where 1 is not included and 2 is included. Well, we have, I think, just enough time to finish C or get close to it. Let's go ahead and do that. We have factorial here that's going to cause a bit of a problem, but nothing the ratio test cannot handle. As a matter of fact, factorial can be simplified really well by the ratio test, because you see, n plus 1 factorial is n plus 1 times n minus 1 times n minus 2 and so on and so forth, and n factorial is n times n minus 1 times n minus 2 and so on and so forth. So taking a ratio, we have a bunch of cancellation, and we are going to get on the first factor, n plus 1, and that goes to the denominator. How about this algebraic part? That's going to go to 1. And x minus 5 in absolute value, that's going to stay constant whenever x is given. So what do we get? Constant over infinity, that's going to go to 0 no matter what x value is given. 0 is always less than 1, so we have absolute convergence no matter what x value is given. Consequently, the interval of convergence is negative infinity to infinity. Well, we ended up covering all kind of different types of intervals of convergence except for trivial interval. but that's really trivial. We went through rather comprehensive exercise at